All right, I want to move on just a little bit here now. Let's quickly just kind of look back at chapter 6. We talked about parallelograms, right? Initially, talked about lots of properties of parallelograms. We moved on and talked about some special parallelograms, rectangles, rhombuses, and then combination of both at the same time is a square. Good. And today we're going to go one step further, talk about something different. This time we're going to leave parallelograms, look at some other stuff, some different kinds of quadrilaterals. We're going to look at trapezoids and kites. Okay? All right, so let's take a peek here. We want to be able to use the properties and apply the properties of trapezoids and kites. That's kind of what we're shooting for today. Let's look at some definitions. Now, a trapezoid is a quadrilateral, but instead of parallelograms having two sets of parallel sides, a trapezoid has exactly one pair of opposite parallel sides, but not two. The pair of parallel sides we call bases. The other two sides that are not parallel we call legs. Okay? Make sense? So that's a trapezoid. What's the sum of the interior angles of a trapezoid? 360, just like any quadrilateral, right? If the legs of a trapezoid are congruent, then the trapezoid is an isosceles trapezoid. Now, what does that sound like? That looks really similar to something else we dealt with. Yeah, an isosceles triangle, right?
Yeah.
In fact, look how easy it would be. Describe for me, what would we have to do, maybe, if we had to warp this thing a little bit, if we wanted to turn this into an isosceles triangle? Describe how we might do that. Say it again. Okay, yeah, it's one thing we could do. We could make the legs, extend those up all the way. That would work, sure. What's another thing we could do? What could we do to the bases?
Shorten them so that the legs...
Okay, yeah. What if I took this side over here and I just pushed it over that way? I could create... That's kind of cool. I could create an isosceles triangle. Let's move that down here. Right? So all of the properties, or many of the properties of isosceles triangles, we would expect to also apply to isosceles trapezoids. Because really, they're almost the same thing. It's like if I wanted to take an isosceles triangle and turn it into an isosceles trapezoid, I'm just going to pull apart the legs and extend the bottom base, and then the top base would extend also, right? So what do you suppose, remind me of a property, real quick, of isosceles triangles? If I've got an isosceles triangle, meaning I've got two congruent sides, then what else do I know about that triangle? About the angles. Which angles?
The angles of the sides.
Okay, the angles opposite the congruent sides we call the base angles, and those are congruent, right? Make sense? So wouldn't we expect the same thing to be true then, of course, for an isosceles trapezoid? Well, it is. The base angles are also congruent. Okay? Now, there are two sets of base angles here, though, aren't there? Right? Because the base angles are really, they're just defined as the angles between the legs and the base. But look up here, I've also got a pair of base angles right there. Those must also be congruent, huh? Okay. Questions? Okay. So then we know that if it's an isosceles trapezoid, then we know the base angles are congruent, like we just said. Okay. Something else we know. If we have an isosceles trapezoid, then the diagonals are congruent, just like in a rectangle. Remember, in the rectangle, they were also congruent. Now, look, we see this. I want to point something out here. We see this statement again, if and only if. Okay, remember that if and only if we always think of as being a bidirectional arrow. So I've got these two statements. I've got the statement, trapezoid is isosceles. And I've got the statement, diagonals are congruent. And then that if and only if is just like a bidirectional arrow. Meaning when I see if and only if, I could start with either one of these two statements and end with the other one. In other words, I could say, if the trapezoid is isosceles, then the diagonals are congruent. Or I could say, if the diagonals are congruent, then the trapezoid is isosceles. If and only if could go either way. Okay? Questions on that? Does that make sense? Okay. All right. So then let's use that information. If I wanted to, in this quadrilateral, in fact, they tell us in this isosceles trapezoid, PQRS, they give us the measure of angle S as 50 degrees. If I want to fill in the rest, don't say anything yet. Everybody take a look at that and see if we can come up with maybe two different techniques for doing that. Okay, what's one?
You could take SP and go 180 minus 1, or 180 minus 50.
Okay, now that's tricky. Look at that. To find P, you mean? Yeah, look at that. Now, what's he done there? That's pretty tricky stuff. He's looked at these. We know we have these parallel lines, right? Cut by a transversal. And so what kinds of angles are those? Not linear pair. Consecutive interior. Good. And so we know that if parallel lines are cut by a transversal, then consecutive interior angles are supplementary. Very good. So we know that this would have to be 180 minus 50 is 130. Good. And then I know it's an isosceles trapezoid, so what else do we know? Okay, good. So we know that that base angles are congruent. So here's a pair of base angles, and here's a pair of base angles. Good. Did anybody see a way of doing that, filling out all the angles without having to take advantage of the transversal relationship that we saw? Yes, sir.
You could create an equation.
Okay. Meaning you know those two, right? You know if this is 50, that's got to be 50 because it's an isosceles trapezoid and they're base angles. And what do they all have to add up to?
360.
360, and that's your equation probably, right? So then, if the whole thing adds up to 360, these two combined are 100. How much is left over for the other two base angles? 260. Now, if I've got to split it equally, well, that's 130 apiece, right? Make sense? Okay. Either way, we get to fill the whole thing in. Any questions on that?
Nope.
Okay. All right. What about something like this? What if we want to use properties of trapezoids to do a coordinate proof of something? We've got the coordinates of the four coordinates, so the four ordered pairs corresponding to the coordinates of the four vertices of this trapezoid. They tell us this is a trapezoid. Okay? Or we want to show it's a trapezoid, sorry. If we want to show that it's a trapezoid, what would probably be the easiest way to do that? Definition of a trapezoid. Okay, you're on something. Yeah, definitely.
So use the slope of line segment CD.
There you go.
Compare it to segment B.
Good. Okay, so if we find the slopes of AB and CD over here, they would have to be probably what in this case? We don't know the numbers yet, but what's the relationship going to be? If we want these to be parallel, or if they are parallel, we don't really want it that way, but if they are parallel, slopes will be equal, right? Well, let's check it out. We could find these pretty easily. If we want to find AB, coordinates here are 0, 5, and there they're 5, 0. So if I could just subtract this y coordinate from that one. So I'm going to do 5 minus 0 divided by 0 minus 5. Right? y2 minus y1 over x2 minus x1. And that gives me 5 over negative 5, which is negative 1. Right? Okay, so negative 1. Now, if we keep going with that, let's go ahead and just, oops, hold on. this again, so we'll get out of there. If we find the slope of CD, that's going to give us 4 minus 7 over 7 minus 4, negative 3 over 3. That's also negative 1. So those two are equal. So yeah, we know that those two sides are parallel. Okay. Now, for it to be a trapezoid, what would have to be true of the slopes of the other sides?
They're gonna be parallel.
They're going to be what?
Parallel.
They're going to be parallel?
Equal.
The slopes of the other sides to make it a trapezoid? Say it again, Carolyn. Well, if it's isosceles, the lengths would be congruent. But we're not even really worried about that. We just want to show that it's a trapezoid. So what has to be true of the slopes? Should they be parallel? The other sides? How many pairs of parallel sides are there in a trapezoid? One.
The other sides have to be scaling.
So the other sides have to be, they have to be non-parallel. The slopes must be different, right? Okay, well, let's see if that's what we get. So we know these were parallel. The slope of BC, let's see, BC, that's going to be 7 minus 5 over 4 minus 0, which is 2 over 4, which is 1/2. Okay? Well, what about the slope of AD? The slope of AD is, let's see, it's going to be 4 minus 0 over 7 minus 5. Now that's 4 over 2, which is 2. So that's different, isn't it? 2 is different than 1/2. So these two are not equal. So that tells us then that BC and AD are not parallel. So that does make it a trapezoid, doesn't it? You have one pair of parallel sides and one pair of non-parallel sides. Okay. Make sense? Okay. Remember that when we're trying to talk, and this is, you know this, but let's just reinforce this one point. When we're trying to show that sides are parallel or non-parallel, using coordinates, that's a slope issue, isn't it? Parallel means slopes are equal. If we're trying to show that sides are congruent, that's a distance formula thing, isn't it? Sides would be congruent if their lengths were equal. Okay, one more trapezoid issue we got to deal with. The mid-segment of a trapezoid. The mid-segment is defined as the segment that connects the midpoint of one leg to the midpoint of the other leg of a trapezoid. Okay. Now it does some things. So, well, first of all, we can see that if these are the midpoints are the points that break up the legs into two congruent pieces, cut them in half, right? What do you suppose is true of the slope of the mid-segment compared to the slope of the bases? In other words, I'm looking for some ways that the mid-segment is related to the bases AD. We got base AD, and base BC. What are some ways that mid-segment is related? We know the bases of a trapezoid are parallel. That one's parallel also, isn't it? The mid-segment's parallel to both the bases. That's good. And what about its length? Anybody want to speculate about its length? It's in the middle of the two, isn't it? Yeah, it is. It's going to be the average of the lengths of the two bases. Absolutely. Okay, and we can see that if we draw a little picture, we've conveniently got this one lined up so the bases are horizontal. Now watch this. If I extend a line vertically through the midpoints, wouldn't you agree that in this case the top base is just as much longer, right? Just as much longer than the mid-segment as the bottom base is shorter than the mid-segment. Agree? In other words, another way to think about this, if I were to take a piece of scissors or a pair of scissors and cut down like so, and flip this piece, pivot it around so it filled in right there. See what I've done? I've just created a rectangle, haven't I? right? And the length of the rectangle would be the length of the mid-segment. What's that? Well, what I'm saying is, if I were to, if I took this trapezoid and I cut along that pink line right there, and I took this piece right here, I could pick it up and stick it right down there, right? So it made a. Did that make sense? Right. So the point of the mid-segment is then the mid-segment, being as it's halfway in between each of the vertices, right? It's effectively it would be, well, it's just as much shorter than the long base as it is longer than the short base. So that's what it's trying to tell us. There's two properties. It's going to be parallel to both bases, and its length is going to be the middle, in the middle between these two. It's going to be the average of the lengths of the two bases, right? Which we could see because if I were to trim the long base just a little bit and add that amount down to the short base, I would create a different shape out of this. I would create a rectangle, right? And the length of the rectangle would just be represented by the mid-segment. To make that, I would have to trim the long base by the same amount that I'm adding to the short base. Yes, Caroline?
So that whole drawing thing is just to show that it's,
Yeah.
that what you're saying is that it's longer than that.
Right. It's to show this, that the length of the mid-segment, MN in this case, is just the average of the lengths of the two bases.
Okay.
Yeah, that's it. That's it. Yeah, don't be confused by that drawing.
Okay.
And sometimes I think it's helpful sometimes to train yourself to kind of look at those types of patterns. Where now, could I turn this? How would I turn this trapezoid or parallelogram even into a rectangle? Could I trim it and move some things around? And sometimes it's useful to do. Yep.
So it's another way to prove it's a trapezoid?
Yeah.
Or what,
Yeah, you could. If you're working the other way, conceivably, sure. Question?
What are we going to use it
Well, you're going to use it for like that, maybe. Okay. So say you wanted to make a cake so that it looked good. So the profile of the cake, if you looked at the tiers of the cake, the different layers, they lined up. They just weren't random. They lined up in a nice trapezoidal shape. Okay. Well, if we knew, for example, that the diameter of the bottom layer was 20 inches, and the diameter of the top small layer was 8 inches, then what would we want the diameter of that middle layer to be if it's going to be a trapezoid? It's just the mid-segment, isn't it?
14.
Yeah, it's going to be the average of these two. 20 plus 8 is 28 divided by 2. That's how I average two numbers. Add them up and divide by 2. Gives me 14. Right? Okay. And then we get a nice symmetrical looking cake with legs. All right. So, okay, the other shape that we want to take a quick look at is called kite. This is also not a parallelogram. A kite is defined as a quadrilateral that has two pairs of consecutive congruent sides, but the opposite sides are not congruent. Right? So, for example, and notice it looks like a kite. These top two sides that are congruent are linked together, and the bottom two sides that are congruent are linked together. But opposite sides are clearly not congruent. Are any sides of a kite parallel? No. No sides of a kite are parallel. So what are some properties of the kite? Well, we know some things. We know that if a quadrilateral is a kite, then the diagonals are guaranteed to be perpendicular. And the diagonals in this case would look like the frame of a kite, wouldn't they? Here's the frame that you attach the fabric to on the kite. And of course they would be perpendicular. We know that if we've got a kite, then exactly one of the two pairs of opposite angles are congruent, and one pair of opposite angles is not congruent, always. The pair that's congruent is always going to be the pair that sits between, that connects sides of different lengths, that connects non-congruent sides. So the angles that connect the short and the long sides of the kite, those are going to be opposite angles, and they will always be congruent. But notice that the angles that connect consecutive congruent sides. So the angles that connect the two short sides or the two long sides will never be congruent. Well, because it wouldn't fit, right? If you look at this clearly, if these sides are longer, they're going to have to meet at a smaller angle than these guys will, right? Only these pairs of opposite sides that connect different length sides are going to be congruent, but they always will be. Okay, so there's another property of kites. So we could use that information, for example, if we wanted to know what the lengths of the sides. Say we were given information about the lengths of the diagonals of a kite. We knew this segment here, WU was 20, UY was 12, and then each of these segments were 12 as parts of the diagonal. If I wanted to find, for example, let's say we want to find the length of WX. How am I going to do that? I'll give you a hint. It's part of this triangle. Right? Now, what kind of triangle is that guaranteed to be? It's got to be a right triangle because we know the diagonals of a kite are perpendicular. So it's no, we don't need slope. How do we find, if I've got two sides of a right triangle, how do I find the third side? Yeah, Pythagorean theorem, sure. It's going to be a squared plus b squared equals c squared, right? So I know that 20 squared plus 12 squared equals that length squared, right? So if I square root everything, then isn't this one just going to be the square root of 20 squared plus 12 squared? Right? So that's going to be 400 plus 144. So the square root of 644, whatever that is, put it in our calculators and find that it's 23.32. Okay? That's what we'd end up with if we did put that in the calculator. Okay, but we can find it is the thing. Because we know some properties of the diagonals of this kite. Okay, last one. What if we want to find the sums of, or the measures of all the angles, interior angles of this kite? We're given two of them. We're given H is 132, and we're given K is 60. How could I find the measures of G and J? What's the property of kites that's important here? They equal 360. It's quadrilateral, so they all have to add to 360. There's one important fact. There you go. There's the other one. We know that in a kite, we know that there's one pair of opposite congruent sides, and those are the ones, aren't they? Right? So then how could we use that? If the whole thing adds up to 360, 132 and 60 is 192. So 360 minus 192 is what, 168? That's how many degrees are left to split between those two, right? So what would they be? 84. Split it equally, and we get 84. Make sense? Okay? All right, let's go practice.